And hello, everyone. So welcome to today's computer architecture seminar series. So today we'll welcome Qijing Huang from NVIDIA to give us a talk. So Qijing is a research scientist at NVIDIA. Her research focuses on emerging GPU architecture and the co-optimization of algorithms, mappings, and hardware to enhance the system performance. Before NVIDIA, he earned her doctorate in computer science from the University of California, Berkeley. During her doctorate, he worked on algorithm hardware codesign, HLS-based design methodology, and ILP-assisted compiler optimization and hardware design space exploration techniques. So, Mike is yours.
Thanks for the invite and the intro, Dee. Good morning, everyone. So it's a great honor to be here and share our work across many years of research on systematically and rapidly exploring the design space of an accelerator to improve its system performance. I'll be discussing some of the challenges, some methods we developed in the past, and the results we have achieved so far. So have you ever wondered what it's like to be a computer architect at the forefront of AI? So imagine you're the lead designers that are given the opportunity to architect the next generation AI accelerator for a new tensor algorithm called GPTX. So you'll be presented with a chip area of, let's say, the radical limit size, 800 millimeters square, and the best available DRAM from the vendors. And you're free to fill this chip with either compute resources or on-chip buffers to optimize for performance. And now you'll be facing a very key design challenge, which is how do you provision this chip area among different units, such as storage, compute, and communication components. A straightforward solution would be to perform a design space exploration, assuming you already have a simulator, emulator, or existing RTL to allow you to evaluate different design options. However, if you look at the size of a typical design space, it is very big, especially considering that we need to determine the optimal mappings to fully leverage the benefit of different design points. So in this example, we show for a reasonable ML accelerator together with the mapping space of each design, and assuming a very, very short time to evaluate each implementation. It will still take typically like trillions of logical years to explore all these design options. And as a result, this process is very time-consuming and costly. And the natural follow-up research question is how do we tackle this vast design space? So the first technique I'm going to present here is called like COSA, and this is mainly focused on reducing the mapping space search time for different architecture. So it considers and uses like a constraint optimization based approach to find performant and energy efficient schedules for different architecture, tensor accelerator architecture in one shots. And I'll dive into more details about how we leverage the property of the tensor workload and the tensor accelerator to kind of formulate this scheduling technique. So so this is the work done when I was at Berkeley in collaboration with Professor, my advisor, John, and Professor Sophia. And as I previously show in the slides, the growing complexity in algorithm and hardware kind of pose an intractable space for scheduler. And as scheduling is actually pretty hard, and it's also important, as we can see there is a huge difference in the performance between a good mapping versus a bad mapping, right? And this slide kind of lists the prior state-of-the-art work to tackle this mapping space problem. So we kind of categorize them into three approaches. The first one is brute force approach that aims to exhaustively cover the space. So I list all the related kind of work here. It's a little bit dated, but this was what we know at maybe like 2 or 3 years ago. There are more like tools available now to kind of tackle this space. And the second category is the feedback-based approach, which is data-driven, and it employs machine learning algorithm to navigate the space. And the last category is constraint optimization-based approach that kind of try to formulate the computer compilers design decisions, or like compilers decisions into mathematical optimization problems, and use standard solvers to solve them directly. And many polyhedral kind of framework falls into this category. They kind of use ISL kind of library to do these scheduling to make these scheduling decisions. And among these approaches, I think you kind of can tell that like for the brute force and the feedback-based approach, they're kind of expensive and time-consuming because they require many samples to work. In addition, they kind of can sample from a lot of like invalid space, since the boundary among valid and the valid schedules can not be directly kind of identified using like some like intervals, right? Like the mathematical like numerical intervals, right? So that's not an easy space to draw for the valid mapping space. And lastly, they cannot really generalize to a new search space with new hardware architecture, new problem space, right? And the well-known kind of polyhedral framework, they don't really directly solve critical scheduling decisions either, such as the tiling factor sizes. And in our work, what we're trying to propose is another kind of constraint optimization-based approach called COSA, and you're kind of trying to determine the all the important tensor algorithm schedule decisions in one shot. So, yeah. Okay. So the idea of COSA is to derive from a few key insights of the domain-specific workflow and accelerator design. The first insight is that the key computation of major DNN workflows is very regular. It's dense matrix application and it's statically analyzable, meaning that the loop bounds known ahead of time. And the second insight is that the hardware is not a black box. So we should typically leverage the hardware constraint to help us prune the scheduling space. And lastly, unlike the CPU and GPU designs, many tensor accelerators requires explicit data movement. So it's kind of like software managed data movement instead of like a hardware managed like cache systems, right? So if we kind of directly treat the hardware black box, it might generate schedules that violates the hardware constraints and results in invalid mapping. So with these three insights in mind, we introduce our approach. So the target workflow we have is a tensor dense matrix operation or tensor workflow, such as a convolution, whose computation can be defined with fixed loop bounds. And for example, in this convolution implementation, it can be written in a 7 nested loop as shown in this slide. And the COSA targets accelerator with kind of spatially laid out PEs. It's kind of like a very regular, let's say, n by n and knock, and we assume the SIMD kind of like vector unit implementation of the tensor core inside, and the constraint we can directly express them in the architecture specification on the left-hand side. Note that the overutilization of these resources in our mapping will lead to invalid implementation. So in a software managed accelerator. So given this input DNN dimensions and the target accelerator architecture, we used COSA to formulate scheduling problems into a standard integer optimization problems with typically with like variables, constraints, and objectives. So this is like a typical way to formulate an ILP. And the scheduler will now kind of output the schedule, which can be represented in the specialized loop as I show here. So to generate these specialized loop from the problem specification, our ILP solver needs to determine first the tiling factor sizes for each level of memory hierarchy, the spatial temporal mapping, which determine whether each loop iteration will be implemented serially or spatially in parallel so that we can leverage all the hardware resources. And lastly, we have the loop permutation to determine the data flow, so that to determine the reuse pattern of like which tensor among the three input-output tensors we will be reusing at different memory hierarchy. And the key idea of COSA is to turn the scheduling problem into a prime factor allocation problem and solve for a allocation variable. So here is a very simple example, assuming we have a matrix vector multiplication workload, and its input vector size is 28 and the output vector size is 15. So we're first trying to break this loop into factors, and then we're trying to allocate them into different memory hierarchy. As we've shown here, we kind of trying to allocate some factor of the seed loop dimension into the way buffer, and some of them will be also allocated to the global buffer. And for the k dimension, we also trying to just allocate some of the factor to the global buffer, and the rest of them will be kind of we assume that it will be scheduled to the DRAM level, so it's outside of the way and the global buffer. And here's so once we allocate this, we can kind of also write a constraint here to determine whether there's enough capacity for this allocation to be valid, right? So for example, if my factors within the global buffer size, like the product of them is larger than 20, that means it's invalid schedule. But if it's smaller than 20, that's a valid schedule. And these can be also formulated into a integer linear programming so that it can be directly solved by the solver. And you can see that here it is how we calculate the utilization of each buffers given this assignment of the binary allocation variable. So, and likewise at each memory level, we kind of need to assign whether this vector should be allocated for spatial or temporal execution. We again have additional decision variable, x, so to determine for each vector whether it should be allocated into spatial or temporal execution. And again, we can assign a constraint here to say that there's only a limited amount of parallel hardware units, and therefore that your vector that assigned for a spatial execution cannot exceed that hardware constraint. And lastly, it's the hardest things to formulate, so which is the loop ordering. Likewise, so we also kind of have this kind of allocation variable. So instead of assigning each vector into different memory hierarchy, we just directly trying to also assign them to different rank order within that memory hierarchy, right? So for example, in this case, if we assign factor 2 to the rank 0, that means we were trying to put the factor 2 as the loop bound of the innermost loop, right? So this can be also directly mapped into a for loop. So basically with the 2 as the innermost loop bound, c equals 2 as the innermost loop bound, and then k equals to 5 as the outermost one. So putting it all together, so given our allocation variable, which is out basically once we put it into integer programming, the integer programming should give us a value that's valid for this variable. So this is the target variable we're trying to solve in the ILP. And once it solves this variable, we can directly map it back to a valid mapping that also specifies tile sizes, loop ordering and spatial temporal mapping. And as I mentioned that we can easily kind of determine whether a schedule is valid or not based on whether the assigned factors are smaller than the buffer size constraint we put in the code linear programming implementation. So for example, if we put like a factor of 3 and 2 and its product is 6, and if it's larger than the weight buffer size, it's an invalid mapping. And likewise, we can do the same for the spatial resources. And I want to kind of just mention a special trick here, because you might have already occurred to you that like if you trying to multiply two variables together, it doesn't sound like a linear equation, right? So we actually had a little trick called the log trick to turn the multiplication into an add by directly take the log of the two variables that's multiplied together, right? So if you take the log of product of two variables, it turns into an add of the two variables. And in that case, if we formulate everything in this log domain, it will be linear. So basically, it will be addition of different variables instead of like multiplication of different variables. And this will result in a linear equation that can be solved by the solvers. So a little bit like a side info is that like normally the solver can only solve for either linear or quadratic objectives or constraints, right? So if it's a product of variables plus another product of other variables, it can be very hard to solve. And here I kind of want to mention a little bit on the objectives, right? So once we formulate this, that you can generate a valid schedule that's subject to the hardware constraints, we still wanted to optimize its performance. And there will be different objectives we can devise. One will be the utilization driven, and the other is compute driven, and then there's the traffic driven ones. So due to the time limit here, I'm not gonna take a deep dive here. So I want to mention for the utilization driven ones, we actually later find out this is actually not the best objective to have. What it says is that we want to utilize the buffer capacity as much as possible. Yeah, so which is not a must here, because you don't really necessarily need to utilize all the capacity in order to fully reuse Tensor. And but then compute driven and the traffic driven objective is directly related to the compute throughput, like the maximum achievable compute throughput if we are optimizing for the compute driven objectives, and the traffic driven approach would just be the minimum data traffic to the backing store. So basically this is an objective that directly optimizes for memory driven performance. If you think about the architecture performance, it's either limited by compute or the memory traffic or the network traffic. So if you are minimizing the maximum of either term, it will be leading you to a pretty good overall performance term. And also I'll skip this. And basically once we kind of evaluate them, we kind of see that we can kind of find schedules with higher speed up compared to random. So it's almost like a exhaustive random for us, and compared to time loop hybrid. So we kind of search around maybe 100K valid mappings to achieve the best time loop hybrid schedule. And then you can see COSA kind of still outperform them because we explicitly kind of express these objectives in ILP. And likewise, we can see a significant improvement on energy efficiency. And what's more important for design space exploration is that this leads to a faster time to solutions in the mapping space, so that we can kind of significantly reduce the mapping search time in the design space exploration that basically have to efficiently leverage your hardware to lead that leads to the optimal performance. And we also showed that it also generalized to different architectures. So that's why it could be used for design space exploration. So if we have a mapper that only tailored to specific architectures, that's still like not too useful for design space exploration, because even if you achieve the best performance on an existing hardware, it doesn't really transfer to new hardware, then that will still be problematic. And the next word I'm going to introduce actually targets the architecture design space now, because we assume that mapping space problem has been solved. So we leverage COSA for our map space in this new word called VISA. And we applied an ML-based technique to trying to transform the architecture design space and make it more friendly for the search algorithm to navigate efficiently into the optimal solution. So this one is still done in collaboration with the Berkeley researchers, and it's more on the researchy domain. So it's kind of like a little bit like idea to try out instead of like a practical kind of solution that will directly implied that can be directly applied to the real design space exploration, because we kind of want to understand how to apply ML effectively for architecture design space exploration. So there are some challenges when we trying to tackle this architecture search space. So first one is that it's you can basically from its input I list here, right? First, there are many parameters to be tuned for the architecture design templates, right? So in this case, it will lead to like a high dimensional space. And then the second one is that a lot of them are discrete. So the number I show here is kind of like only like a discrete number. But then, for example, there are also other options saying that what topologies of your network you should be using, whether you want to do systolic rate-based PEs, or do you want to do like vector-based PEs? Those are more discrete kind of space. But still, like with all these decisions, you can still see a hardware design space of like pretty big size. And the next the challenge we're facing is that like when we trying to optimize for hardware design, there are always multiple objectives, right? So we want to get to the lowest latency plus the best energy efficiency. And you can see if we kind of sweep the hardware space, so the x-axis and the other horizontal axis are just different, the buffers percentage for the accumulator and the number of PEs, right? So you can see with respect to the different hardware designs, the energy performance is actually not a smooth space, right? It's pretty non-convex, and we also don't just want to optimize for energy. We need to kind of optimize for energy and the latency at the same time, with latency maybe being a slightly more important goal, right? So that's the second challenge that we face. So the performance space of this search is not a smooth space, and it's not convex. And if we take a look at the prior search strategy for architecture design space search, a lot of them are like heuristic driven, guided by designers' intuition. There are some black box optimization approaches that directly search in the space, assuming your hardware, again, is just a black box, and just employ different efficient search algorithm to speed the search up. And there's also this last gradient-based optimization approach, so that you kind of need to train a performance model in ML, and then you rely on the gradient to optimize your hardware design. There's also an RL-based approach that you just design an environment, also like a performance model, and then you train your RL agent to navigate a space more efficiently. So it's since your agent has some learned model, so hopefully some of the intuition can be applied to a new problem, for example. And you don't really treat your hardware or the problem space as a black box. But instead of, so there are the pros and cons of each approaches. Despite the difference, so I'm not going to mention them in more details, this word list here all kind of have one thing in common. They kind of trying to focus on developing strategies to explore the original search space. But as we learned before, kind of certain nature of the original space will make it challenging for many search strategies to be effective, especially the ones that requires low dimensionalities and smoothness of the design space. For example, like the Bayesian optimization and the gradient descent. All right, so our thought was that can we just generate a new design space, that one that is more friendly for existing search strategies to perform well. So what we want from this design space, right? So we first want the new design space to have low dimensionality. So we can kind of easily visualize and analyze the data we get and navigate the space with more knowledge we have from visualization, right? And second, we want to the performance surface to be smoother so that the search algorithm can work more effectively. And last, we want the design space to be reconstructible to be back to the original design space. So we can map the optimal designs and to the original space for evaluation. And now we have identified the desirable properties of the space. The question is, how do we achieve those? And what we thought about the approach is that we can kind of train a variational autoencoder to perform such new design space construction and reconstruct the new design space back to the original space. So what is a variational autoencoder? So here's a little bit background of it. So it is a feed-forward model that predicts output X prime from the input X through a bottleneck layer with reduced dimensions. And the training of this encoder-decoder network can minimize the mean square error between the X and X prime. So as a layer, the bottleneck layer Z after training, it becomes a lower dimension representation of the input X. And what makes this model variational is that the encoder network predicts the mean and standard deviation for a normal distribution. And the latent point is directly drawn from the distribution. And this way, more points in the latent space can be corresponding to one of the original points once you sample from this low dimensional latent space. And very popular application of VAE was the image synthesis, right? So the variational autoencoder can learn the underlying latent features by identifying the structure in the data. And in the example image of the people's face, the latent feature might encode whether the person is smiling, whether the person wears glasses, and the user can kind of vary these latent features to generate different faces. So you get to control the generative output by tuning this low dimensional feature space. Another interesting and related application actually is that like the researchers in chemistry also have successfully used them to explore new chemical designs. They actually are ahead of us. They already published this paper in 2018, right? So they have trained in VAE for non-moleculars and kind of jointly trained with another predictors on molecular properties from the latent space. They then identified latent space area with different properties and trying to pick the latent points. They have the feature that they desired and decode them to new molecule designs. So our work is very much like inspired by this work, right? So we are designing computer architecture instead of like a new molecules, but we still want the computer architecture to be efficient, right? So we have certain properties we desire. So different from the prior work. So our goal is to actually learn a new compressed and reconstructible latent space that we can help accelerate the design space exploration on. And just like the VAE pipeline that I showed previously, VISA kind of still like provides a transform search space for hardware design space through the encoder. And we kind of perform the search on this latent space instead of the original input hardware space. And now you might be curious on how we exactly train this VAE to obtain the latent space with some performance semantic attached to it. So here is how we train this pipeline. So first, we gather a data set of hardware configurations and the corresponding latency and energy labels for different DNN layers. We feed the hardware configuration as input to the encoder and produce the corresponding latent space features. And along with the VAE, we introduce a latency and energy predictor, which directly take the latent space feature as inputs, and as well as the DNN layer configuration as inputs, and and estimate the energy and the latency. So we will have another loss here to show how accurate this predictor is. And then we pass this latent representation of the input configuration through the decoder to predict the output hardware configuration. And then we gather the input hardware configuration as the label for the output of VAEs, and also gather the actual latency as labels for the performance prediction from the latent space. And then we add the loss of the VAE and the loss of the predictor up as our training loss. So the reason why we train this predictor along with the VAE is that in this case, we could provide more performance information for the VAE training so that you can structure its latent space design based on this latency and energy properties. And now you might wonder how the designs are arranged in the latent space. And here we took a 2D visualization in the VISA to visualize it. So you can see on the figure on the very left-hand side, the color represents different properties. Represents the magnitude of different properties of the hardware design, and the first two figures shows how the design with different number of MAC units and global buffer sizes are arranged in the 2D latent space. And the last figure shows how the design with different actual EDP, which is energy delay product, are organized in the 2D space. We can see pretty good clustering and structural in this plots. And the last figure specifically also shows that by adding the predictor into the VAE training pipeline, it can rearrange designs inside the latent space such that the points with similar EDPs that can get closer to each other. And we also visualize the latent space to understand how different hyperparameters work. I'll skip this. And another thing we study is like how many dimensions do we really need in the latent space to fully capture the input and output features. And from this study, we kind of showed that maybe I think 4. If we have as long as we have like 4 different dimensions, we should be very close to the original. So basically, we will reach a construction loss of pretty low, so that we can safely say that like it kind of captures most of the hardware design space features we have in our training set. And here's like a visualization we have with respect to the predicted and the actual energy, and this. Oh, sorry, the latency. Sorry, and we can see that this is for the latency, this is for the energy, and we can see that the performance predictor kind of did also a pretty good job. It kind of roughly matches what the real latencies are, and it kind of creates some smooth surface, like some smooth area within the space. So it's hopefully a little bit easier for us to navigate this space compared to the high-dimensional original input space. And now you have seen how it trained, and now next I'm going to briefly go over how it's getting inferenced. So there are two phases we have in our search. One is exploration, and the other is exploitation. So since we need to, so basically for inference, we only start with the latent space, as I mentioned before. And here we have inference pipeline. So basically, once we find it, design points in the latent space, we directly decode them to the hardware configuration. And we directly map a DNN layer using COSA to this hardware configuration to evaluate its real latency and energy. And here, once we have these latency and energy feedback, we can actually imply either Bayesian optimization on the latent space to sample the next point, or we can directly use the gradient descent. Let me show. So for the Bayesian optimization, it just basically has this internal statistical model to approximate this non-performance model, and you use like acquisition function to decide which to sample next. And Bayesian optimization typically operates well in the search space of dimensionality of like lower than 40. And what we did here is that we kind of directly use Bayesian optimization as a black box optimization on the latent space and keep sampling to get data points that's better and better. And here we show the results that it kind of improves. If we do Bayesian optimization on the latent space compared to the original space, it gets a better performance and a higher sample efficiency. The other search that we use is that we directly leverage the performance predictor in the latent space and perform a gradient descent. So here is not really a black box optimization on the latent space. It's actually a gray box optimization you can think of, right? Because we assume we already know the performance on the latent space using this ML-based performance predictor, and then we perform a gradient descent on this latent space with the performance predictors gradient. So in that case, we can directly use the gradient on the latency or energy predictors to find performance points on the latent space and decode them for the real evaluation. Sorry, this one. So again, I think this one also shows a higher efficiency when we are doing gradient descent on the latent space, which is the blue curve. It gets to the lowest performance, like a lot, like a few sample, like I think 30 samples earlier. So every sample kind of contains a few, like 200 evaluation on the predictor. And then these are the real samples we use the real kind of like mapping and the simulator to gather. So in this case, you can see that if we're doing gradient descent on the original space versus if we train a performance predictor directly on the original space, it still kind of shows higher sample efficiency. So with that, we kind of showed how we kind of devise kind of complex design space or like architecture space, new architecture space embedding you can think of, and to accelerate the search, and how we kind of leverage different search algorithms to leverage this latent space for a faster sampling, or for better sampling efficiency. And now it seems that we have kind of successfully addressed this design space exploration challenges with the two technique, which can reduce the search time and the cost for both the mapping and the architecture search space. However, we actually did not really know what we learned from this search, right? So still, without a very exhaustive search, we don't know if the resulting designs are truly the optimal designs for what we target. And the other question is, how far are they from the best possible solution? And this is very important because we kind of need to know the limit in order to know how far, like what's the margin we can optimize, right? Even though this gives us better better and better designs and better mappings, but you don't know if it's optimal, then the question here is like whether it's worth spending more time into this area to kind of trying to further improve it, right? And second, it's like how much gain we're gonna get from further improving it, right? So basically, in this case, every time there's a new algorithm technology or new metric come along, we still need to kind of develop a new simulator or implementation and redo this search, right? So this kind of leads to a very long development cycles just to assess the benefit of different kind of hardware features. So as an alternative in the real world, we actually just normally turn to like a simpler, like a mathematical or analytical models. One example would be just the roofline model with speeds and feeds analysis to develop like that very fast design intuition so that we don't have to rely on all the simulator infrastructure that we mentioned before. And this analysis is also like generalizable to all different new algorithms if it can be expressed in this format, right? And it's typically carried out using more algorithmic properties of the workflow itself instead of like a specific mapping or implementation of them. And for example, if we're doing the speed and feeds analysis for the roofline model, what we usually do is that we trying to calculate its operational intensity. So for every workload, we first analyze its operational intensity, which is the total number of computes of an algorithm divided by the tensor size of all the operands. And by looking up the roofline model with this operational intensity, we can kind of easily decide whether we need to add more compute resources or increase the memory bandwidth to improve the performance, and whether there's but still, this doesn't tell you how much gain you get if you're adding more bandwidth or more compute. Oh, sorry, I think it still gives you this still gives you how much gain you get by adding more bandwidth if you kind of tilt the slope or also raise the compute roof line, right? So this is why this kind of model is useful and generalizable, but it doesn't give you any details. And a pitfall here is that when we're doing the roofline model calculation, it actually doesn't tell you any buffer storage trade-offs in the analysis. So you only have this DRAM bandwidth and then the total compute throughput. And basically, we still don't know in this case that like, although the roofline model tells you how much more bandwidth you need to add, you still don't know how much buffer storage you will need in your hardware in order to improve your current design performance, the current design's performance. And if we take a step back and think about what's missing from the previous analysis, it might occur to you that like when we do the real workflow implementation, we always cannot assume that you always only load the operand of the algorithm only once, right? Because you don't have a limited buffer size on chip for an architecture. And by ignoring that, basically that we cannot reach this algorithm minimum access on the off-chip DRAM kind of creates a huge gap in our modeling when we're doing this analytical kind of analysis. And here's kind of like the work that we have trying to kind of bridge this gap so that we can reach a tighter bound for our performance model. And so we can understand how the data movement varies with the buffer capacity we provision on chip. And this is a kind of lower bound limit. So meaning that there shouldn't be any mappings or implementation that will reach a data movement that's lower than our bound, given a different buffer size constraint. And Here's an example showing how actual backing store access at different memory level for matrix multiplication kernel on GPUs differ from the algorithm minimum. So if we're only taking into account of the tensor size of the matrix multiplication, we kind of normalize it to the 1 times. But in reality, if you take a look at the DRAM to L2 traffic, it's 6 times of what the algorithmic minimum tells us. And if we look at the L1 and L2 traffic, it's 32 times more, right? So the actual backing store access and the operational intensity we use to look up the roofline model normally would depend on the mapping and the buffer size, as we show for the mapping problem before, right? And a desirable data movement bounds that we want is the one I show here, so that for each target tensor algorithms that can be expressed in an Einstein notation shown on the left-hand side. The x-axis of this bound, it will be the buffer size on chip, and the y-axis of this diagram will be the amount of traffic to the backing store that is achievable with any mappings. So for all the cache expert here, it's not a missed curve because it's not derived from a single mapping implementation, but many Pareto optimal mappings. And then we refer to this curve as the ski slope diagram as the data movement always monotonically decreases with the buffer size increase. And with this diagram, we're now able to answer a few important architectural design questions. So the first question is basically, given a buffer capacity, what is the minimal attainable data access count to the backing store? As demonstrated with the gap 0 on the slides, it could be orders of magnitude away from the algorithm minimum that we can directly calculate from an algorithm. And as shown with gap 1, we actually don't need to buffer all the operands to achieve the minimum backing store access count. And this diagram will tell you how big of a buffer you will really need to achieve the best reuse of your data. And the final question concerns how the workload benefits from incremental increase in your buffer capacity, which can be addressed by looking at the rate of change on the ski slope curve. So now I hope I have convinced you that this diagram can provide very valuable insights into the design space exploration. And this brings us to our contribution, basically a effective way to generate these curves. So we call our approach just orogenics, which stands for mountain creation. And this is how we create this mountain. So first, we kind of trying to find a tractable mapping space so that we don't have to do exhaustive search on a huge, high-dimensional architecture search space with all the architectural details, right? And then the second one is that we're trying to avoid a mapping search for different algorithms and different architecture, right? So sorry, for different hardware architecture with different buffer sizes. So what we did here is that we kind of have an abstract architecture with a simple 2-level surrogate structure. And we call this architecture snowcat architecture. So we assume that we have a buffer with unlimited capacity. And this simplicity of the architecture leads to a smaller map space on which we could perform as exhaustive search on. And to address the second challenge and avoid separate mapping search for every possible buffer capacity, we just use the following methodology. So given an input tensor workload, we define the ISOM. We perform an exhaustive search on the snowcat architecture with unconstrained buffer sizes. And for each mapping, we kind of gather the data access count and use the buffer utilization of each mapping to represent the corresponding buffer capacity requirement. And this ski slope curve is then this Pareto optimal frontier of different mapping points. And once we have derived this data movement bound shown in this diagram, we can simply take its inverse and multiply it with the total compute to obtain this operational intensity bound, so that the operational intensity grows together with the buffer sizes until a point that there's no more reuse we can exploit from the buffer. And now let's take a look at some like example that our Genesis can do for 3 different gem shapes. And each of them is labeled with 3 numbers representing the size of each dimensions for the matrix allocation. So here are how the data movement and operational intensity bounds for the 3 gems. So first, we can look at the different shapes so first, like the different shapes of the gem can result in different slopes in this diagram. And we also observe that these bounds all decreases in a power law manner. And by looking at the operational intensity bounds, we also had a very interesting findings, which is that the maximum effectual buffer size, meaning that the buffer size that's basically beyond which that we're not able to obtain more reuse, is actually the smallest tensor operand size within the gem. So for example, if you have like a 16K by 1K by 1K gem, the smallest tensor will be size 1 megabytes. And that's why our operational intensity of this gem plateaus at the 1 megabytes. So meaning that if our buffer is larger than 1 megabytes, we won't see an increase of the operational intensity. So meaning that if we increase the buffer capacity, we're not gonna reduce the data movement of this algorithm anymore. So the buffer increase, the increase in the buffer capacity will not result in a lower data movement or a better memory bound performance for this algorithm. And we can also kind of use it to demonstrate what is the best mapping regions, right? So what is the best data flow under different buffer capacity constraints? So again, the x-axis is the buffer size, and the y-axis is the backing store access achievable with different buffer size for a given gem shape of 16 by 1K by 1K dimensions. And we can see that I kind of highlight the region that kind of demonstrate what is the best data flow. So when we see that when the buffer size is smaller than 0.5 megabytes, which is half of the smallest tensor, it kind of indicates the optimal mapping kind of always prefers the upper stationary data flow. And once your buffer size is larger than half of your tensor size, then it kind of suggests that the waist tensor stationary data flow is more preferred, right? So kind of this kind of like ski slope diagram can kind of provide you a lot of like data movement information, as well as like the best mapping hints if you want to implement new mappings for your new architecture, for example, with different buffer sizes. And yeah, so it reviews pretty powerful design and mapping insights. And the second thing we're trying to look at is that like we always feel that the fusion is a pretty big space, and there are a lot of techniques trying to tackle this fusion space, but we still don't know what's the limit we can get with fusion, right? And basically, we want to also vary the buffer size and see how fusion benefit from this varying of buffer size and whether fusion is always beneficial. So I kind of skip on what the details of fusion and jump ahead to the results. So basically, sorry. So we kind of devise fusion tiling, fusion optimization, meaning that instead of like processing a gem fully at a time, we assume that we process a row of the gem at a time, and then we move on to the next gem so that we can kind of enable what we call the tile fusion. So we don't fully compute a gem to enable fusion for the current gem, but then we actually just compute a row, for example, or a column of the current gem to enable fusion. So basically, we're trying to exhaustively search all those different tiling space for fusion so that we can better leverage the buffer capacity constraints we have on our system. And you can see first, we have the purple curve baseline for a chain of 6 operations in the GPT block without fusion, and there's the green curve that's applying the tile fusion optimization I mentioned, and that imposes mapping constraints on the on the intra-layer mappings. And basically here is how it compares to the no fusion case. So we can see that when we try to enable tile fusions, it's only beneficial when we have a larger buffers to enable both the intra-layer and inter-layer reuse. Because again, I want to mention that if we want to enable fusion, it has to kind of enforce the data flow of the two different layers that's relevant. They have to enforce the data flow of these two layers to be concordant with each other, and that limits its intra-layer search space and results in maybe higher usage of your buffers in order to reach the same backing store access. But once if your buffer reaches certain capacity, fusion will become beneficial. And basically, our tool is basically trying to analyze the best case scenario for fusion and unfuse so that the compiler engineer can use to determine whether they should consider fusion given a buffer capacity in the system. And for architecture designers who also kind of think of like how big of a buffer we should enable in the design so that we can reach the minimum backing store access and the lowest energy. So we kind of want to show that this kind of approach can help us comprehend very complex workload optimizations and help us reaches the limits we can achieve with different constraints, especially the on-chip buffer constraints. And I think we're running out of time here. So I kind of just wanted to leave with this slides. Basically, once we know this bound, we can directly use this bound to derive a performance model, which I'll skip. So basically, instead of using the roofline operation intensity as input, you can use our buffer size as input, and then it will outputs the performance. So it's an enhancement to the roofline model, which you take the algorithm and you take the buffer size for an algorithm, and the y-axis is directly the performance, basically, yeah. And we kind of design another like very straightforward kind of approach by deriving the roofline model for a GPT fuse layer, and then we trying to just draw a model this performance in assuming there's a limited resource for compute and limited resources for memory, and then we kind of derive this what we call another mountain-like curve to kind of help us identify there's actually a convex point in your buffer area ratio compared to the compute in order to reach optimal, what we call optimal architecture for performance. Yeah, so that concludes this part of the talk. Sorry, this one's a little bit in a hurry, so if you have any questions, I can take it offline. Yeah. And basically, with this one, we kind of want to show that this kind of like bound-driven analysis is a kind of very radical and new design approach that help us make decision in early stage design space exploration, and it can help us visualize and offers insight on how much benefit we can get with different let's say mapping strategies and different buffer to compute ratios in this case. Yeah. So that kind of concludes my talk, and I would like to thank everybody for attending this. And if you have any questions, I will post this presentations. I'll share it with G, and then hopefully there's something useful for your research you can leverage from them. Yeah.
Oh, yeah, thank you. Because now we are kind of running out of time, so probably we can have at least maybe at most one question. Any question from audience?
So I have a quick question.
I can ask.
Okay.
Okay. Brandon, please going first.
Yeah, thank you, Jenny, for the interesting talk. I have a quick question regarding the last work. So you mentioned that there's one very interesting diagram that you show is for a certain threshold of the buffer capacity, right? Mm-hmm. And the data flow selection would be leaning to either weight stationary or the output stationary. Mm-hmm. But based on my current understanding is the buffer size is used to determine your capacity constraint, right? You can either is the tiling constraint for different matrices, right? So it highly depends on the workload, right? Because you can assign the tiling factor for either input, output, or your weight. So why we can make a conclusion is that the buffer size will determine the selection of the output stationary or weight stationary. It's not depend on the workload.
Oh, it is dependent on the workload, sorry. So every workload will have one of this diagram, sorry.
Oh, okay, I see.
But
Okay.
I kind of trying to generalize the insight for a gem, let's say, right? So if it's a gem shape workload, then it's likely it's kind of like this kind of shape, and then assuming there's no parallelism, because so this is like a very abstract model in the hardware, right? So basically what we observe is that like when you reach half of your smallest tensor size in your buffer for a gem, then it's kind of switching from output stationary to the smallest tensor stationary kind of scheme. So that's just one insight we get from analyzing the results we get from the exhaustive kind of search of the mappings and abstract this buffer size from it.
Okay, thank you.
But it's for different workload. If you have a convolution, you will need to do it again and see what's the best insight there.
Yeah. So it also depends on the dimensionality of your input matrices, right?
Yes, that's why I said it's smallest tensor stationary. So it's like it depends on which of your like if it's your input smallest or output stage smallest, or it's also like weight smallest. Yeah, it really depends.
Okay, may I ask one more question regarding your password, the second one? So you mentioned there are multiple options for the accelerator designs, right? We can do either systolic array, spatial accelerator, or vector machines. So how do you consider their architectural impacts on the performance when formulating those analytical models or search models?
Oh, that's a good question. So for those ones, we actually don't have mathematical models.
Okay, I see.
Has to be done in simulation because I think a lot of trade-off it's really like the efficiency of your innermost vectors, like how it's like the how it leverage. So it's really related to the circuit design level things, right? Like whether it's efficient to do like systolic array and whether it's area it costs like smaller area to achieve the same throughputs, and there's a lot of like circuit level details need to be considered in that, like choosing of like SIMD versus like systolic array versus other spatial architecture kind of things. Yeah, and also the programming model will also be very important there, right? So whether you're allowed a vector kind of like flexibility of like scheduling a vector at a time, or it has to be like a matrix, that kind of thing. So so it's not too much on it cannot be directly reflected on the mathematical model, I would say. It's more lower level optimization that we need to consider, and we can directly extract the energy numbers and area numbers of different design inside our higher level design simulation to consider those. Yeah. So it's like it will be simulated.
Okay, thank you.
Okay, cool. So we actually do have more questions. If you don't mind, Jenny, if you're okay to stay longer, we can maybe also answer these questions. And for the audiences, if you have other things, feel free to drop. It's a little bit over time, of course. Yeah, we have one question from the chat. So like the examples of the slider for beard emotions, etc. for the image autoencoder, where you are able to identify what the latent dimension in your work presented, or what input hardware configuration has the most impact. I guess that's the second question. So this one matters more. What the input hardware configuration had the most impact on the latent space and are most important for predicting the performance. So which hardware configuration is most important for latent space and also the performance prediction?
I see. So that's a very good question. So in fact, so if you recall that actually the hardware configuration is not directly reflected on the latent space. So latent space, let's say if you have two-dimensionality, we actually don't know which hardware configuration they represent, but I think if you're talking about which hardware configuration has the most important effect on predicting the performance, I would assume that that should be definitely the parallelism, right? Like how many PEs you have, definitely it's one of the critical features because that affects your compute bound performance. That would be one. And I think the trade-off among different buffer sizes will be also important, but it's a little bit more complex because because of like different interactions of different memory level of like reuse of data and stuff like that. Yeah, so I would say if the number of PEs, the number of like MAC elements within the each PEs, those are the most important ones. Yeah.
Okay, thank you. So I saw our audience raise a hand. Would you mind speak up and talk about your question?
Oh, sure. Thank you, Jenny. Thank you for the talk, by the way. Really amazing work. I really like the last one, the Orogenesis work. And I have a question, So in that one, you took an example with the snowcat architecture. What are your views on scaling up this methodology for a multi-level memory architecture? Do you think like a roofline plot, we might have to draw the roofline, like as we draw the roofline at different memory levels, we'll have to do the ski plot at different memory levels as well. And what do you think? What kind of information would it give us? Would it be some useful information or yeah, what are your views?
Okay, that's a very good question. So indeed, as you said that for the schizo diagram, I would say that you can use it for different memory levels. If you can basically assume that you just draw a line into your memory hierarchy, right? And then you'd be like the line above are the aggregated buffer capacities that we consider. And then what we provide in our genesis would be the minimum achievable data movement to the outer memory hierarchy levels, right? So that would be how we could use that. But there's a caveat here, as you mentioned, for multi memory levels, right? So what happened is that like it actually will again imposes a little bit more constraints on the hardware or on the hardware, right? So in this case, some of the mappings we found for the optimal backing store access, assuming we just randomly draw a line, and there are, let's say, like two memory hierarchy inside what we use for the aggregated capacity, then some of the mapping we found might not be valid for the ones with two memory hierarchy inside, right? So that's why what we provide a lower bound, I would say, in this case, because if you have more mapping constraints due to your like more like deeper like memory hierarchy, then basically if you have more constraints, that means that your bound might go higher. And in that case, that's a caveat. So we only provide a lower bound in this case. And there's a way to get the exact bound, which is you just directly add memory hierarchy in your snowcat sweep, but then that results in a much longer, like exhaustive search time on that to find the bound, right? So, but if you only have to do it once for the workload you care about, it's still worth doing, I would say.
Okay.
So that they can find optimal points. Yeah.
So if I think about a multi-level, if I may ask one more question, if for a multi-level architecture and let's say I want to go with a snowcat architecture for a multi-level architecture, would I consider the L2 memory as the one buffer in the snowcat or the L0 as the uh, one buffer? I don't know if I was able to explain my question. Let's say if I build my question is basically if I build a snowcat architecture for a multi-level architecture, right? Would I consider L2 as my buffer for the snowcat, or will I consider L0 as the buffer for snowcat?
Oh, so I would say you can do multi-level lookup, right? So it's
Oh,
if
okay.
you're doing the L0, you just use L0, and then what the snowcat shows you is the L0 to the L1 traffic, if it's all inclusive. And then if you draw a line at the L2, then you can just make the let's say the capacity of L2 as your L2 plus L1 and L0, I would say, right, as your inner like buffer capacity, and then our genesis bound will be the L2 to DRAM traffic incurred in this
Got it. Okay. Thank you. Thanks a lot.
work. Yeah. Thanks for the good.
Thanks for all the questions, all great ones, and of course for the talk. Excellent. So any more questions? If no, let's thank Jenny virtually. And thank you for giving us a wonderful talk. So hope to see you in the future. And thanks everybody for attending as well.
Yeah, thanks for the great questions and nice to be here.